Our speaker, Dr. Robert Pappalardo, is a senior research scientist at Caltech's Jet Propulsion Lab, or JPL for short. He did his undergrad at Cornell and his PhD at Arizona State, and he went on to his first working positions as a postdoc at Arizona State and Brown University. He later became an assistant professor at UC Boulder before finally ending up at Caltech. His research focuses on the possibilities of oceans under the ice of Jovian moons, and he currently works for NASA overseeing the scientific goals of a probe to be sent to Europa called the Europa Clipper. So please help me welcome Dr. Robert Pappalardo.
Thank you very much. Thank you for coming tonight. And I want to especially thank Kevin Lee for setting up this visit here. Yes. Pleasure to be here to talk about some of my favorite moons. There are a bunch of icy moons in the outer solar system, not just Europa, which is up front and the one I study most, but other moons of Jupiter, Saturn, Uranus, Neptune. And out there in the outer solar system, it's pretty darn cold. And so a principal component of these moons is water ice, the same kind of ice you have in your freezer, and some other ices too, like ammonia and methane and nitrogen and carbon dioxide. But it's not just as much as I like to think geology of these moons is incredibly fascinating. What interests the public most, the real driving reason for exploring these moons is that we think that many of them probably have oceans underneath their surfaces. A question that people have been asking for a long time is, are we alone in the universe? Is there other life out there? And Mars is an obvious place to look, though it's not clear if Mars is still hospitable to life. Whereas the interior oceans of icy moons may be the best place in our solar system and beyond to search for life. We're not talking whales here. We're probably not talking fish, but we're talking single-celled organisms. So we'll talk as the talk evolves. We'll look at the possible environments out there, what they might be like, some of the evidence that there is liquid water out there, and we'll take a tour of some of these guys. But first, we'll start at home with our planet Earth and think about what defines a potentially habitable environment. Searching for life is a pretty tough thing to do with a spacecraft mission when we don't really know exactly what we'd be looking for. Would you recognize life if you came across it out there in the solar system, on Mars or on an icy world? So much of what we go after is trying to understand habitability. Are there environments out there that we think, if you were to take an Earth organism and put it out there, it might be able to survive? Or from what we know about the conditions where life can survive on Earth, can the conditions on other worlds, are they in that same realm of pressure, temperature, salinity, radiation, etc., where what we know about life on Earth tells us, yeah, there are organisms that can live in that kind of range of conditions. So when we're talking about habitability in the solar system, I should ask if there's a laser pointer so I can point if the desire emerges. Thank you, Kevin. When we're talking about habitability, we're really talking about searching for the ingredients for life. Perfect. Thank you so much. Great. So I see the top's getting a little cut off. The so-called ingredients for life. And by that, we mostly mean a solvent. Liquid water, the universal solvent, is the one that we're usually talking about, but we'll see some other interesting examples as well. We want, because when for metabolism to happen, there needs to be chemical reactions. For chemical reactions to happen, there need to be some sort of medium, some sort of solvent. We need the right kinds of elements from which life is built. Things like oxygen and hydrogen and carbon and nitrogen, phosphorus, sulfur, the things that are most plentiful in organic molecules. Now, it could be we're talking about some weird life that uses other elements, right? Star Trek fans might remember the Horta silicon-based life. But we want to start by understanding life as we know it. We want to if we're looking for life elsewhere, we're really looking for life as we know it. And then when we get to a place like Titan, as we'll talk about at Saturn, then maybe we can stretch our imaginations a little bit farther. A hard one here is chemical energy. That is, life can live in very extreme environments on Earth. There's life in hot springs at Yellowstone that lives on chemical reactions between iron and hydrogen. That's not the kind of thing we do when we respirate. It's not the kind of thing plants do when they photosynthesize. But there are lots of other chemical reactions that don't need light or don't need an organism to eat another organism. Chemosynthesis, chemical reactions that can power life. So when we're talking about chemical energy, we're really talking about chemical disequilibrium, the desire for chemical reactions to occur which can power life. And then we're talking about a stable environment. It's not so good if there's liquid water that's around for a few years, or maybe even a few thousand, or maybe even a few million. We don't really know how long it took life to get started on Earth. We don't really know how long a stable environment is needed. But if you had liquid water and then it froze up, well, so what? Unless that life could go into other niches and no longer needs liquid water. So that one will come up too, especially in the context of Enceladus at Saturn. So let's take a look at our cast of characters a bit here. Hopefully, if I step away from the mic, you can still hear me somewhat. So we're talking about the outer planets, Jupiter, Saturn, Uranus, Neptune, not to scale, and their largest moons, for the most part. Now, these moons are to scale with each other. At Jupiter, there are 4 large moons, the Galilean moons, first seen by Galileo over 400 years ago. Whoops. Wrong button. There we go. Io, Europa, Ganymede, and Callisto. Well, Io is mostly a rocky world, has lots of volcanoes. It's cool. It's part of the story, but it's not one of these icy moons that might have an ocean. But Europa, Ganymede, and Callisto are, and we'll talk about them a bit. At Saturn, there's one big guy, appropriately named Titan, and we'll talk about it a bit. You're not seeing the surface here. You're seeing a smoggy atmosphere at Titan. We'll see what that smog is. At Uranus, there are a bunch of little moons. We'll talk about the kind of medium-sized moons. We'll talk about those later on. And Neptune has one big rogue moon, and that's Triton. And just to give you a feel for the scale, we shouldn't forget Pluto, no longer a planet, downgraded, dwarf planet. You can get the feel of Pluto compared to the other worlds. But up in the upper right corner is our moon. So that'll give you a feel for the scale here. Europa is about the size of Earth's moon, and that's not too different from Triton or Pluto when we're talking about the scale here. But Ganymede, the solar system's largest moon, is larger than the planet Mercury. So if these things were orbiting the sun instead of another planet, they'd be planets on their own right, the largest ones at least. So these are the guys that we'll see close up in pictures and talk about a little bit. Europa, Ganymede, and Callisto at Jupiter, Enceladus and Titan at Saturn. We'll touch on Triton at Neptune as well. Now, another piece of the story that will come up a little bit is that it's not just, as I mentioned earlier, it's not just water ice, but ices and oceans in the solar system is the title here, because there are other ices that come into play. And the further out in the solar system that we go, the more volatile the ices are. The things that would be gases here at Earth, it's so cold out there that they can condense into solids. So out at Triton and Pluto, out in the Neptune system, nitrogen, which is the main component of our atmosphere, would freeze out onto the surface of Triton at 40 degrees Kelvin. So in the Jupiter system, there's not just water ice, but there's carbon dioxide ice. And then in the Saturn and Uranus systems, not only is there water ice and carbon dioxide, but also ammonia, carbon monoxide, and methane, and then nitrogen ice by the time we get out to Triton and Pluto. So let's start in the Jupiter system with the Galilean moons. As I mentioned, first seen by Galileo in 1610. There's his little drawing. And then here's the Galileo spacecraft named after him, which from 1995 to 2003 orbited around Jupiter. And with every orbit around Jupiter, it would make a close flyby of one of these 4 Galilean satellites, these moons of Jupiter. So let's take a look first at Europa, the one that I'll argue is really most promising for life in our solar system. It's a bizarre surface, really like no other moon. Unlike our moon, we don't see lots of craters when we look at Europa. You can see a few. Here's one, Quill or Puch if you're Welsh, although I had a Welsh person in my audience recently. She said, that's not how you pronounce it. Very few craters tell us that this is a relatively young surface. So Europa is 4.5 billion years old. It formed when the solar system formed. But something has repaved Europa and gotten rid of the large craters since. By the number of large craters that are there, we can say that the surface of Europa is on average about 60 million years old. So since the time dinosaurs roamed the Earth, Europa's surface has been paved over somehow. That tells us it's probably still geologically active today. We can zoom in to Europa to see it close up. A bunch of Europa is bright with these lines crisscrossing it, and we zoom into an area that looks like that, and that's what it looks like close up. Bizarre place. Again, really like nothing that we see on Earth. You're seeing big ridges crisscrossing the surface. That's, almost 2 kilometers across. There's a scale bar. In the background are lots and lots of other ridges and grooves, some dark, many of them bright. And we'll come back and touch on those here in a minute. And then there are some areas that are dark and kind of mottled and sort of looks like hamburger or something. And you can see these older ridges here that have just been destroyed in place, like something has cooked the surface from below. So what's going on to make that chaotic looking terrain? Well, what's going to keep something like Europa orbiting Jupiter? What could possibly... Oh, my movie isn't looping. No, loop movie. I'm just going to have to hit it a lot. Why would Europa be geologically active today and maybe have an ocean under its surface if it's only as small as our moon? The smaller an object is, the quicker it loses heat, the more surface area to volume it has. So something the size of Earth's moon has lost its heat over the age of the solar system. It's not warm anymore. But Europa, we think, is still geologically active today. That's because there's a heat source out there that our moon doesn't have. Europa is orbiting Jupiter. Whoops, sorry, things are a little cut off. Orbiting Jupiter in a somewhat eccentric orbit, somewhat egg-shaped orbit. It gets a little closer and a little farther from Jupiter as it orbits around. And so when it's a little closer, it gets a little stretched out by Jupiter. And when it's a little farther, it contracts a little bit. In fact, we think that Europa probably flexes by about 30 meters as it orbits around Jupiter every 3.5 Earth days, every 85 hours. So it's getting flexed. And like bending a paperclip back and forth, that flexing generates heat. And if you bend a paperclip back and forth and you're careful not to break it and you touch it to your lip, you can feel that it heats up. So it's frictional heating. It's the same kind of thing. So Europa is being flexed as it orbits around. Got to keep clicking that. And not to scale here, but it's flexing by about 30 meters, and that creates heat inside of Europa. In fact, it creates the most heat where Europa is warmest on the inside. So at the bottom of its ice shell is where we'd expect most of the heat to be input. If the interior of Europa is also warm, the rocky part of Europa is also warm, then that might be heated up as well. Now, why do we think there's an ocean? That diagram had an ocean in it, but I'm just assuming it. Well, one can do a calculation of how much tidal heat should be generated from this flexing, and it's enough that there probably should be an ocean within Europa, but there are a lot of uncertain factors. We're not sure from the calculation, but there are observations from that Galileo spacecraft that are pretty convincing for an ocean within Europa. Some of them are geological, and we'll look at a couple, but the best evidence is that Europa kind of set off the Galileo spacecraft's metal detector, in a sense. So Europa is moving through Jupiter's powerful magnetic field. Europa is orbiting around through this very powerful magnetic field of Jupiter. And from Europa's perspective, because that field of Jupiter is tilted, Europa is seeing Jupiter's field change as Jupiter orbits. So Jupiter's field kind of flip-flops as seen by Europa, simply because Jupiter's magnetic field is tilted. I'll follow up with the astronomy students. We'll talk more about that tomorrow. And so what Europa is doing is creating its own little magnetic field to counter Jupiter's magnetic field. And what the Galileo spacecraft measured is the magnetic field around Europa was oriented one way during one flyby and oriented another way during another flyby. That doesn't sound very normal, unless Europa is creating its own magnetic field to counter Jupiter's magnetic field. Well, what that tells us, if Europa is creating an induced magnetic field, as this is called, there must be something conductive inside of Europa. In the shallow subsurface of Europa, there's a conductor, something that conducts electricity. So what the Galileo spacecraft saw is a sign that there's something in the shallow subsurface of this icy moon conducting electricity. And the predictions from tidal heating are that there's an ocean down there. And so what probably the magnetometer was seeing is evidence of a salty ocean beneath Europa's surface. So we want to confirm that. It's very indirect evidence for an ocean, but it's the best evidence that we have right now. We want to go back with a spacecraft that will literally measure that flexing of Europa to confirm that there's an ocean there. Because if there's no ocean, then the flexing will only be about 1 meter. And if there is an ocean, it'll be 30 meters. It'll be obvious if we can measure that flexing directly. Let's go back and look at some more cool geology. I mentioned I'm a geologist by training, so let's see why I'm concentrating on that stuff. It's all about the geology. This is one of these double ridges that crisscrosses Europa's surface. Just bizarre. The light's coming from here. It's a ridge, and then a big dip, and then another ridge, and then a shadow of that ridge. So we're zooming into some of the best Galileo spacecraft images of one of these ridges. These things are all over the surface. There's no consensus as to how they're made. Most common feature on the surface, we don't understand how they form. There are lots of different ideas. Maybe water is literally coming out and sloshing over and making this. I think more likely something's pushing up from below. Or another idea is that, like the San Andreas Fault, there's strike-slip motion. One icy plate moving past another. And that may somehow create a ridge and create heat in the subsurface, which pushes the surface upward to form one of these ridges. So we're not yet sure exactly how water might be involved in making those ridges, but there's a suspicion that water might be involved or might be made at ridges. Like rubbing your hands together generates heat, more of this frictional heat idea, that could even create melting along ridges. We're going to look at Enceladus in a little while, which has very similar ridges, and those are associated with places where water vapor is escaping from we think from the ocean of Enceladus. It's possible that something like that is going on at Europa as well. Europa also has these freckles all over its surface, or Latin for freckles is lenticulae, so that's what they're really called. They're about 7 kilometers across on average. And what we think is going on, whoops, am I missing my slide? Sorry, hold on. There it is. What we think might be going on to form these guys is that big blobs of ice are coming up to the surface from the base of the ice shell where it contacts the ocean, where the ice is warmest, where tidal heating is input into Europa's ice shell. So it's kind of like a lava lamp. Maybe I'm dating myself with lava lamps here, but they're back a little bit. The light bulb heats the wax, and the wax rises up, and then it cools off as it rises, and it sinks back down. And that might be what's going on here. The ice is heated down here. It rises up buoyantly because hot stuff rises. It's less dense, cools off, and the ice sinks back down. And this is a model of that process by Amy Barr, who's now at Brown University, looking at the ice-ocean interface here, the very cold surface here. Did I mention Europa's cold? 100 degrees Kelvin, minus 280 degrees Fahrenheit is what we're talking about at the surface of Europa. So that warm ice is rising up and then sinking back down. It's a challenge to figure out actually how this stuff can get out of Europa, how it can break out of Europa. It might be because tidal heating concentrates in the warmest ice. So as the ice rises, tidal heat concentrates in that warm ice and so can keep rising instead of just cooling off and sinking back down. Europa has this dark reddish stuff all over the surface, and that may tell us something about the composition of its ocean. Well, to start with, it has bright white stuff, and that stuff is ice. And that ice is irradiated from particles trapped in Jupiter's magnetosphere. Jupiter's magnetosphere is incredibly powerful. If charged particles are in there, they get accelerated and rotate as fast as Jupiter does, once around in 10 hours. And these very energetic particles slam into Europa's surface, slam into the ice, and break apart the water ice. So H2O breaks apart into H and O, and the O sticks around on the surface, and the H floats away. And so Europa's surface, at least, is charged in oxidants, things that contain a lot of oxidants, things like oxygen, things like hydrogen peroxide, things like that. That if they can get into Europa's ocean would be a wonderful fuel for life that could actually contribute to chemical disequilibrium and perhaps feed life. Now, the dark stuff itself, so I'll show you some of these squiggles, show you what all this means. This is looking at how Europa reflects light at various wavelengths in the infrared. We can see out to about here, this is red, but then we get into infrared beyond where our eyes are sensitive, but we can fly instruments that are sensitive at those wavelengths and measure the fingerprint of what wavelengths of light get absorbed by the surface, and that tells us something about what the surface is made of. So when we see dips like this and like this at these very particular wavelengths, people do this for a living, say, oh yeah, water ice. That means water ice. That's easy. But there are other dips that are subtly different when you look at this reddish stuff. So it's red in the visible, but what's going on in the infrared? Slightly different. It's just been displaced. Don't worry about the fact that one's higher than the other, but the shapes are a little different. These are a little shallower and a little more asymmetric than the water ice. And you wouldn't notice this necessarily, but a spectroscopist would. And some of the best fits to this stuff are when you take magnesium sulfate or Epsom salt and put it at very cold temperatures. It's a pretty good fit to this red stuff when seen in the infrared. So this magnesium sulfate or Epsom salt may tell us what's down there in the ocean. That is the kind of material that could be conducive to life if it's down there. But there's also this stuff is also a pretty good fit, and that's battery acid, sulfuric acid hydrate. That wouldn't be too good for life, so not as nice to take a bath in. What might be going on is that the magnesium sulfate is from the ocean, whereas the battery acid may be made on the surface of Europa from this radiation. Take ice and magnesium sulfate and irradiate it, and the sulfur and the oxygen and the hydrogen can get together in different combinations and make this battery acid stuff on the surface. So it's a hard problem, this stuff coming from below, we think, and stuff that's created on the surface. So again, with a future mission, we want to try to get at some of the freshest stuff, some of the smaller patches, and have a better, with more sensitive instruments, have a better indication of what this dark reddish stuff is on Europa. We haven't seen evidence of organic materials on Europa's surface, but they're destroyed very quickly by radiation. So it's kind of a conundrum. Maybe there's organics. We're not seeing them. It doesn't mean that they're not down there, but maybe they're destroyed very quickly. And with a future mission, we can look for evidence of organics and maybe try to find some fresh spots on the surface of Europa. So let's take one last zoom into Europa's surface at one of its coolest surface features. And here X marks the spot of a type of terrain aptly named chaos, as you'll see in a minute. When we were planning these images, and I was working as a postdoc at Brown, I got a call from a colleague and friend at Ames Research Center. He said, "Bob, we need to target the red bunny." I'm like, "What are you talking about, Jeff?" And he said, "You know, the red bunny, the upside-down bunny." And so we retargeted some images that were supposed to be elsewhere on Europa and made a strip across here to see what this dark splotch was. And we're zooming into higher and higher resolution images that were obtained on various Galileo orbits. And you start to see this dark stuff looks like the surface has been broken up. And what it is that those ridged areas have been broken up, not just to look like that hamburger stuff, but like big blocks that have moved around and jostled. And here we go into those images that my friend and colleague argued we should take, showing these big blocks that look like blocks of sea ice. This one's about the size of a small city. It's about 5 kilometers across here. These are kind of interstate highway size, those grooves. As we zoom into some of the best images of Galileo's tour at Jupiter, it starts to look like a place. It starts to look like Monument Valley out in Arizona and Utah or something. Big cliff faces and then shallower slopes. Again, very few craters, some tiny ones. Some of these are secondary craters, stuff that was thrown out of the impact from Quill. And now, panning around as much as my computer can refresh there, you can see some of that more hummocky, hamburger-like stuff. Here's another block. Here's a ridge that has seen better days. What we think, and this is kind of iceberg size. It's about 1 kilometer across. What we think is that, again, some heat source from underneath caused the surface to just crumble in place. And the thought is there may have been melting under these areas. A recent paper from a couple of years ago suggests that there may be lakes within the ice created by concentrated tidal heating that melt out, a big lake the size of something like Lake Superior, inside the icy shell of Europa and cause the surface just to collapse down to make those chaotic regions. So those are the kinds of places that we would want to go to explore to see if there's liquid water today inside Europa's ice shell, to understand how far down beneath an ocean is, and to see if it's geologically active today. Someday we might want to put a lander in a place like that and scoop up some of that red stuff and see if there's organic material in there and see if there might even be some sort of signs of life. So this is just kind of a summary of Europa's ice shell. We think it's about 20 kilometers thick, though that's highly debated, and some of the various features on the surface probably about 80 kilometers of liquid water based on the gravity data, based on as the Galileo spacecraft flew by Europa, we could tell something about how centrally condensed it was and how layered it is. So we think there's an iron core, a rocky layer, and then that about 100 kilometers of H2O, some of it liquid. So to sum up the ingredients for life at Europa, we think that it has the key ingredients. Water, more than twice all of Earth's oceans if you take 80 kilometers and figure it about over Europa's globe. The essential elements. Well, we don't know yet the detailed chemistry, but impacts certainly bring in things like carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Those should be there. We think they're on Ganymede and Callisto. Where are they on Europa? Europa's been repaved. They're probably down in the ocean. They've probably somehow been stirred down into the ocean by geologic processes. Chemical energy. We think oxidants are made at the surface, which would be a great fuel for life. But what about the other half of the reaction? For those of you who remember your chemistry, you need reductants. You need oxidants and reductants. Those are the two things that get together to make chemical reactions. Well, if the mantle of Europa is hot, if the rocky part is hot, then maybe Europa's seafloor might look something like places on Earth's seafloor where there's hot rock, volcanic activity, and where water gets down into the rock is superheated, charged with chemicals that go pouring out onto the ocean floor in what are called black smokers. They make these chimneys. What this stuff is minerals just condensing out as they hit cold water. Wonderful source of reductants. If Europa's seafloor is active, if there's a way of getting oxidants from the surface into Europa's ocean, then Europa would have the chemical energy needed for life. So right now that's speculation. We need to go there and find out. And as I alluded to, Europa as a big moon has probably been simmering for 4 billion years. We don't know how long the tidal heating has been going on. We don't know if it's been around for 4 billion years, but we suspect it may have. In fact, it may go through up and down stages, and that's something we need to understand more by understanding the Jupiter system as a whole. So, and there's new news at Europa that you may have heard. Back in December, a team of researchers using the Hubble Space Telescope found this at Europa. Found that Europa, in some of their observations, was glowing in its southern hemisphere in hydrogen, emission of hydrogen. That is, there was a concentration of excess hydrogen off of Europa, and oxygen as well in the same place. Hydrogen and oxygen suggest maybe there's a bunch of water coming off and being ionized, being ripped apart. So instead of H2O, it's hydrogen and it's oxygen, and it's glowing in the ultraviolet, which they detected. So the idea here, I'll show the little, see if we can make the little movie work. Come on. Oops. Oh, my newest movie, and it's not going to work for me, is it? Oh, well. This is just showing an artist's depiction of Europa and a little plume shooting off and a little happy Europa drifting off there. So we'll see Enceladus in a little bit at Saturn, which we know has plumes, stuff jetting off of the surface. It's possible that Europa might as well. If that's the case, we wouldn't need a lander to understand what's going on in terms of the chemistry of underneath the surface of Europa, if there are organics that get destroyed at the surface, say, by radiation, because they may be pouring out in these plumes, and we could just fly through them with a spacecraft, like Cassini has done at Saturn, and measure what's down there, understand what the subsurface chemistry is at Europa. If we found evidence of heavy organics, we'd sure want to go back with a lander and analyze more carefully, or even do a sample return and bring some back to Earth. So I always spend too long on Europa. So here we are, more than halfway through. So I will try to rush through some of the other guys. Ganymede, largest moon in the solar system, probably has a subsurface ocean as well. It doesn't have as much tidal heat. It's farther from Jupiter. It's not heated as much. The orbit isn't as eccentric either. But the magnetometer from Galileo, that metal detector, if you like, the conductor detector, says there's a conductor in the subsurface of Ganymede too, but it's deeper, more like 150 kilometers. Well, what do you know? 150 kilometers is exactly where it's pretty, or 170. It's pretty close to where an ocean is predicted to exist within Ganymede or within Callisto, as we'll see in a minute. Ganymede and Callisto differ from Europa in having a lot more H2O, a thicker water layer, ice layer. This white bit here, the H2O, the ice plus water, is much thicker than we saw at Europa. And what happens when water, H2O, is under pressure is that it actually transitions below liquid water. It's squeezed into other forms of ice. Now, only the chemistry students will probably really get excited about phase diagrams here. This is depth. Let's cut it off a little bit. Depth inside Ganymede or Callisto, they're about the same size. So pressure increases that way to the right. And this is temperature, higher temperatures up there. Well, this is the melting temperature of ice in our freezers, 273 Kelvin, 0 Celsius, 32 Fahrenheit. But under pressure, ice actually melts at a much lower temperature, about 250 Kelvin, instead of 273. And not only that, it forms these other weird types of ice. The ice in our freezer is ice 1. There's also ice 3 and ice 5 and ice 6. And for you Vonnegut fans, there is an ice 9, but hopefully it won't destroy the world. So what happens inside these bigger moons is that instead of there being an ocean all the way down, water all the way down, at the base of the ocean, pressure squeezes the H2O so much that it forms a different kind of ice. Higher density types of ice, ice 3, ice 5, ice 6. So what you end up with is an ocean sandwich at Ganymede and Callisto. Regular plain old ice on top, and then these higher density kinds of ices below. So this isn't as attractive for life because where your black smoker is going to be. You can't pour nutrients from the hot rock into the ocean, at least not directly. Also, this ocean is predicted to be about 150 or 170 kilometers down below the surface, and that fits the magnetometer data. So there's not going to be a lot of exchange of material between an ocean that's 150 kilometers down and the surface. So the ocean of Ganymede isn't as attractive for life, but it's still pretty exciting that these big moons may have oceans. The life would have to live under much higher pressures than at Europa. Europa, we're talking pressures similar to Earth's oceans, to the deepest part of Earth's oceans. Ganymede also has very cool surface geology that we'll talk about another time. Callisto is kind of the boring moon. We think the interior it never even got hot enough to separate rock from ice. So it's probably a mix of rock and ice in Callisto. Its surface, the most exciting thing that happened in terms of the geology is it's probably been evaporating carbon dioxide over the age of the solar system. It's a boring place, but once again, evidence from the magnetometer of a subsurface ocean. How could that be? Callisto hasn't been warmed. It's not tidally heated. What we think must be going on is that there's some sort of antifreeze in Callisto. Salts or maybe even ammonia. Callisto being farthest from Jupiter has the best chance to have gotten more volatile ices, things like ammonia when it formed 4.5 billion years ago. And as we'll see when we get to the Saturn satellites and beyond, ammonia is a very effective antifreeze and might keep a liquid layer going inside of Callisto. Now, moving on to the Saturn system. A beautiful picture of Titan with Saturn way in the background there. It's blocking some of the rings of Saturn. As observed from the Cassini spacecraft, which is currently orbiting around Saturn. Cassini has now made over 100 flybys of Titan. It's in its, I'm losing track, second or maybe now third extended mission. So NASA has been extending it, which is wonderful, and they're going up for one last final extension very soon. And every time it makes a flyby, it learns something more about Titan. Well, it also had a probe, the Huygens probe, that was launched off and went through the atmosphere of Titan, measured its composition, pressure, temperature, etc., going down through Titan's atmosphere, and actually lived when it crashed onto the surface, and took some pictures, as we'll see in a minute. Titan is a very smoggy place. You can't see the surface. Its main atmospheric constituent is the same as Earth's main atmospheric constituent, which is nitrogen. But its next most common constituent is methane. And so in a methane-nitrogen atmosphere, when things like ultraviolet and radiation, there's not so much radiation, Titan, but there's some, hit it, it breaks apart methane and nitrogen and makes smog. So Titan is a pretty smoggy place. But it also makes things like complex organic molecules that rain down onto the surface. So it's cold enough at Titan that it was able to hold on to methane. Methane was out there at Saturn during the time Titan formed, and that's why it's so different and so weird. Because if you have methane around, you can break apart the CH4 and the nitrogen and make all kinds of complex organic molecules. If you have C, H, and N around, those of you who've taken organic chemistry know you can make all kinds of interesting molecules. Well, how do we learn about Titan's surface without being able to see through the clouds? We can barely see through in some longer wavelengths, but really you have to go out into the infrared to see down to Titan's surface, or radar, as we'll see in a little while. This is the infrared first. So infrared light can penetrate the clouds and reflect off and be detected by Cassini's infrared spectrometer. So you're getting some idea that there are surface features. The dark stuff is mainly sand dunes. There's some sort of organic sand, we think, down on the surface. There are various kinds of ices as well, carbon monoxide and carbon dioxide on the surface of Titan. There's some evidence of impact craters on Titan as well. There's some big ones. So this is illustrating what I was talking about a minute ago. Smoggy nitrogen, methane atmosphere. Ultraviolet light comes and breaks up the methane. Some of the hydrogen escapes. Some complex molecules like acetylene and other solids form, and it makes this haze of ethane, which is what we can't see through. There are clouds of methane and nitrogen at Titan, and there are some molecules that are made that rain down onto the surface. Now this says rain evaporates before reaching surface, but now we know some of the rain sure does make it to the surface. We think that there are pools of methane and acetylene on the surface. Methane and ethane on the surface of Titan, as we'll look at in just a minute. This was actually a predictive diagram. It's wonderful. This is before Cassini and Huygens, and it's all right. So you saw a little bit about what the infrared imager saw. This is what the radar was able to see. Radar can penetrate right through the clouds and bounce off of the surface. And you can see very clear evidence of things that look like river channels. And you can see this thing, this dark area, which sure looks like it has shorelines associated. And while I was working with Cassini, I was its project scientist during the first extended mission a few years ago, we were still debating Were these old dried up seas, lake beds, or did they have liquid in them today? And one of the best pieces of evidence, come on, let's see, let me skip this and I'll come back to it, was this. One of the Cassini scientists realized that we could test for whether there's really liquid at Titan's surface today, these methane, ethane lakes. Was that thing really filled today? If the geometry were just right and we looked for a glint from sunlight off of a lake and up to the spacecraft. And he looked at all the data of opportunities that were coming in the next couple of years for when the geometry would be just right to measure such a glint. And that's what was seen here. This is a glint off one of the lakes on Titan's surface, really demonstrating that there must be liquid there today. There have been, since, a couple of other means, like it was just announced, a detection of waves on one of the lakes, very shallow, very small wavelength waves. This is a map that was very recently released of Titan's northern hemisphere. So North Pole up here, blank areas are where there's no radar data. This is false color, like colorized blue parts that where we think that there is liquid in lakes on Titan today. And you can see that Minnesota has a run for its money in terms of the number of lakes here in Titan's northern hemisphere. Very few in the southern hemisphere. There's one prominent lake in the southern hemisphere, though there has been evidence for areas that darken and then brighten again. Evidence for active rain of methane and ethane on Titan's surface. So you could just see the possibilities for exploring Titan in the future to understand what's in these lakes and what do they tell us about the origins of life. So this is that photo I was talking about from the surface of Titan. The Huygens probe made it all the way down. It wasn't sure when it was designed, would it splash into some sort of liquid or would it hit the surface? It did hit the surface. These are, they're small boulders, the ones that we see in the foreground here, looking off to the horizon. They're somewhat rounded. That means they've tumbled. These are ice boulders that have presumably been washed and tumbled and rounded by fluids. What we think Titan might be able to tell us in terms of astrobiology is it may be able to help us understand the origin of life here on the Earth. So one idea is ancient impacts might have made temporary water pools because, we're not talking liquid water at the surface. But then again, maybe methane and ethane as a solvent might have allowed the rise of some weird kind of life. One can imagine if lakes of organic molecules are sitting around for millions of years on Titan's surface, would there be some sort of natural selection? Would some sort of primitive biology be able to get started at Titan's surface? People have speculated about hydrogen and acetylene being the oxidant and reductant in a reaction that could power life on Titan. So it's very interesting to just think about the possibilities for some sort of weird life in the lakes of Titan. Now, can't leave out the fact that Titan, like Ganymede and Callisto, probably has an ocean down below its surface, down there at 150 or 170 kilometers. And because we're way out there at Saturn, and we know there's ammonia that should have formed when Titan formed, ammonia can lower the melting temperature of ice in an extreme way. Instead of ice melting at 273 Kelvin, instead ice will melt at 173 Kelvin if there's lots of ammonia around. And if there's a little ammonia around, it can melt at something like 250, or depends on how much ammonia is there. But ammonia is a very effective antifreeze that can lower the melting temperature and allow for an ocean inside of Titan, as we think there probably is today. And again, there's some indirect evidence from the gravity field at Titan for an ocean down there today. Now, an ammonia ocean, again, doesn't sound as exciting for life, but life on Earth can stand a little bit of ammonia. So these are the guys we've talked about so far. Ganymede, Callisto, Titan, deep oceans, maybe cold oceans. Europa is the attractive one, having an ocean in contact with a rocky floor. But then there's one more here, tiny little Enceladus. And you may have just heard a little about Enceladus in the news. So let's look at Enceladus at Saturn before I run out of time here. Here's Enceladus, again, rings far in the background there, but here it is. The sun's coming from practically the other side and lighting up almost the other side of Enceladus. And like when you drive into the sunset and there's dust on your windshield, you can't really see because the light's coming through very fine particles in a dusty windshield. We see them when the sun is coming through them. And with this kind of geometry at Enceladus, you see something weird going on there? Those are the plumes of Enceladus. Here they are, seen closer up. Oh, and again, my movies aren't looping. Darn you, PowerPoint. These are not really the plumes themselves moving, but instead the geometry is changing from frame to frame in this just 3-frame movie. But that gives you an idea. There's one big plume here that's made of little tendrils, little jets that are coming out of the surface of Enceladus. And where are they coming from? They're coming from things that look like this. These dark areas, these dark, somewhat bluish areas. This is false color, but these areas are where all these little sources for those jets are. It's thought that water is coming up along fractures that are going all the way down to the ocean to an ocean at Enceladus, tapping that ocean, and some of that water vapor is escaping to space. These things are called the tiger stripes. You can imagine why, informally. And the Cassini spacecraft has a thermal instrument, can measure heat, and these things are so hot, in quotes, that it can measure heat associated with them. Hot meaning the surface should be something like 60 degrees Kelvin at the pole of Enceladus, but instead gets up to over 140 Kelvin. That's hot for an icy moon. It's where the vapor is escaping from the subsurface. Recently, this is what caused some news. That the Cassini scientists were able to use 3 flybys of the Cassini spacecraft by Enceladus to understand its gravity field. And there's a lot less gravity down at the South Pole, relatively more at the north. And we know there's a big depression at the South Pole of Enceladus, so it's not surprising that there's a low in the gravity and how much it tugged on the spacecraft down there near the south. But what they were able to do is actually say that the topography, they were able to compare the gravity to what we know about the topography. And the topography should actually mean that there's even more of a low in the gravity signal down here than was observed. So what would compensate is if there was something slightly denser, something like water, slightly denser than ice, about 30 or 40 kilometers down below the surface. Consistent with the idea that below the very hot south polar region of Enceladus, where this activity is and where the jets are streaming out, is a subsurface sea. A sea that is concentrated around the south polar region. Actually, based on that latest data, that sea should come up a lot higher, being just about 30 or 40 kilometers below the surface of Enceladus. That might make it a very attractive place for life. Again, it's an ocean in contact with rock where it can get chemical nutrients. but it might be an ammonia-rich sea. We don't know how well life would do there. And the other thing is that Enceladus is putting out so much heat that it can't possibly do this for very long. It can't possibly be in equilibrium. And the idea is that it might be having a big burp of activity right now, and then it'll die off. By now, I mean these 100 million years, and then it might cool off again. Is that long enough for life to get going? We just don't know. We've got to go back and try to find out. Cassini is still making flybys, but there's only so much that can be done with the instrument suite that's there. Some people have proposed, let's fly through those plumes and bring some of that stuff back home. I thought I had it on one of my slides there. Did it disappear? There we go. What's in that plume? We know there's lots of water. We can measure it by flying through with a mass spectrometer, as is on Cassini. There's also measured nitrogen, carbon dioxide, methane, and some simple organics, acetylene and benzene, are in Enceladus and pouring out at us. So again, if we could go there with a spacecraft that could measure even more complex molecules with better instruments, we might look for more complex organics even than that. So Enceladus, ingredients for life, probably South Polar Sea, probably connected to the surface by fractures that contain water. So Enceladus seems to have the water. Essential elements, we can measure them. We know they're there. There are simple organics in the plumes. Chemical energy, we don't know yet. We're really just understanding, is there overturn? There's not the radiation environment to create oxidants at the surface. Maybe that ocean is cold. We don't know if it has a warm, rocky interior in there. So question mark there. Stability in the activity might be transient. But again, it's still in its infancy, our understanding of Enceladus. So last but not least is Triton at Neptune, going all the way out to the distant reaches of the solar system. Triton's a bizarre place. Again, not many craters, sort of reminiscent of Europa and parts of Enceladus, and just bizarre-looking features that suggest diapirs, like blobs of warm stuff, like at Europa. There are things that look like volcanoes on ice volcanoes at Triton. There are dark streaks that seem to be geysers. Before there was Enceladus and now Europa, we had seen from Voyager images back in 1989 these dark streaks that seem to rise up from the surface and blow through the very, very thin atmosphere of Triton. It's possible that Triton might be tidally heated today, not because it's an eccentric orbit, but because of a different type of tides related to the obliquity of its orbit. I wanted to just mention Pluto and the middle-sized bodies. If they have ammonia, so smaller objects like the moons of Uranus, here's Triton for scale, and we get into some Kuiper Belt objects. Eris, Pluto, now a Kuiper Belt object. Sedna, Titania and Oberon are moons of Uranus, and Rhea, a moon of Saturn. It's possible that these larger moons might have enough heat from radioactive decay that if they have ammonia, there might be able to be oceans within them today. So it's sort of in the realm of speculation, but it's possible that some of these objects, when I say Kuiper Belt objects, we're talking kind of like the icy asteroids well beyond Pluto's orbit, but Pluto counts as one of them. So Hollywood helped here because the total might mean that there could be as many as 13 oceans in the outer solar system. Europa, its warm, salty water ocean. Ganymede and Callisto, these sandwiched oceans at depth. Titan, being unique in having methane, ethane lakes on its surface, also probably an ammonia water ocean below. And then those middle-sized guys that might be able to have oceans if they have enough ammonia. And little Enceladus, which is tidally heated and may have a South Polar Sea. Earth is the odd guy when you look across the solar system in terms of where water is. It's the odd one because the water is right there at the surface. And the search for life in the solar system in the past for habitable environments has been, where could there be liquid water at the surface? Well, now we know we might have been asking the wrong question. Instead, the liquid water oceans may be below icy surfaces where it can be warm. And these places might be incubators for life. So as I mentioned there and in the introduction, I'm what is called the project scientist for a mission concept called the Europa Clipper. The idea is that we would make many, many flybys of Europa with a spacecraft that's in orbit around Jupiter, kind of like Galileo did with the Galilean moons, or kind of like Cassini is now doing with Titan. But the challenge at Europa is this extreme radiation environment. The Galileo spacecraft just dipped into the extreme radiation environment a few times. It did make a dozen flybys of Europa in total through its extended mission. We're talking about 45 flybys, and we're talking about a mission that's designed specially to try to understand the distribution of water and get at these issues of habitability, get at the issues of water, chemistry, and energy. So stay tuned. We're hoping that might go forward with a launch sometime in the early to mid-2020s. And there are also a lot of fascinating concepts for follow-up missions for Cassini out at Titan. Ideas include balloons, because Titan has this thick atmosphere, orbiters to understand the surface better, and maybe even a lake lander to go to one of these hydrocarbon lakes and understand its chemistry and to tell us what Titan can tell us about the origin of life out in the solar system. So I'll stop there and take questions. Yes.
Titan, what's the explanation for the only the north side, the northern hemisphere having the lakes?
Is really not understood why they're concentrating in the north. We thought at first that it might be a seasonal effect, and we might see it flip, because Cassini's been there long enough. It got there in southern hemisphere summer, and now we're moving toward northern hemisphere summer. It's northern hemisphere spring. And it was wondered, would the lakes fill up in one hemisphere than the other? But they really seem to be concentrated in the northern hemisphere, and we don't really know why that's the case. We're slowly learning, like the lakes that are there, we're getting ideas of their topography, and they do seem to be all at the same level, or very similar level, so it's thought that they're connected through, well, groundwater is the wrong word, but ground fluids are seeping through, and so these lakes are all sort of at the same level. And maybe for some reason related to global topography, they're not forming in the southern hemisphere, but we really don't know why. There's one whopping big one the size of Lake Ontario down in the southern hemisphere, but they're not plentiful. Yeah?
In regards to the slide with the 13 oceans
Yeah.
on it, why does it seem like the oceans are prone to the small moons and those small Kuiper belt objects instead of bigger planets?
Oh, so we've used up the big ones. So the big ones are prone to having oceans. Europa, Ganymede, Callisto, Titan. So Titan and Ganymede and Callisto are the biggest three. Then it goes Europa. Then Triton's the next biggest. So we've just used up all the big ones. All the big ones seem to have liquid water oceans. The medium-sized ones would have oceans only if there's lots of ammonia around. So then you get so small that there's not enough rock. There's not enough heat from rock to melt out oceans in even smaller ones. So let me back up just a second. So for Europa, it's tidal heating that's doing it. That might be true at Ganymede too. Callisto, it seems that it's probably antifreeze that's doing it, ammonia or maybe salts. At Titan, it's antifreeze. At all these guys, it's antifreeze. And then Enceladus is so tiny that it should be frozen up by any means. But it's so extremely tidally heated that it can have an ocean. So if we went back to that first slide of the talk, we don't get, we're out of moons pretty much. So here they all are. And once you get down to the tiny ones like Mimas here, it should be frozen up. Sorry, that's not Mimas, that's Miranda. Mimas is the one inside Enceladus. So tidal heating is the main thing that we think can maintain a liquid water ocean, but if there's ammonia around, which serves as an antifreeze, then some of the smaller ones can have oceans too. So we don't really know that there are 13. There could be as many as 13. We're pretty sure there are 5 or 6, depending if you count Triton. Yeah. So Enceladus is the one with the certain geysers, and it's so small that it doesn't have enough gravity to keep those particles around. So most of them drift off. Some of them fall back, but it doesn't have enough gravity to hold on to those molecules. So the ice particles will fall back to the surface. The gases, though, just drift away. And there's a big ring out at Saturn at Enceladus's distance that has been supplied by the jets. So what it does, instead of making an atmosphere around Enceladus, it makes a big ring around Saturn. That's not how the rest of Saturn's rings form, but this one in particular, there's a ring at Saturn at Enceladus's distance around Saturn. Now, Ganymede and Callisto are as big as Titan, so you'd expect, why don't they have atmospheres? They certainly have enough gravity to have held on to an atmosphere. Well, a couple of things. They might have had atmospheres early on and then lost them slowly to space through time as molecules just drifted off. And Titan's unique because methane is a heavier molecule. There probably wasn't methane around Ganymede and Callisto to make an atmosphere. But Titan is in a cold enough environment that methane, which is very heavy, and nitrogen, stuck around and created this atmosphere at Titan, which hasn't drifted away through time. Enough gravity plus cold made for an atmosphere. Ganymede and Callisto may be temporary atmospheres that went away. Europa, there's a tiny atmosphere at Europa, mostly from these charged particles hitting it and shooting off into space around it. It's 10 to the minus 12 of Earth's atmospheric pressure, a picobar. Very, very thin atmosphere. But enough that we saw those Hubble images of the hydrogen glow. That's essentially part of the atmosphere of Europa. Very, very thin atmosphere. In the check shirt there, yeah.
So you said that Europa's surface is fairly new. Is that, and there's kind of a lack of major impact craters. Is that due to the magnetic field around there? Or do we have, I guess what I'm going after more is, if it's under such high radiation levels and we're looking for a good way of finding out what might be just under the surface, an impact that we can fly through would be a great way to try and see what hasn't been irradiated yet. Do we have any way of tracking when a major impact might be, or a way of creating our own major impact to be able to fly through afterwards?
So the big ones that make a crater like Pearl, a 10-kilometer size crater that would shoot a lot of stuff up, would happen every 4 million years. So that we're not going to see that. We're not sure of the rate of smaller impactors at Europa. I should probably use the mic. We don't know how much stuff is out there at smaller sizes. We can see 1-kilometer comets out at Jupiter, so we know how often a 10-kilometer crater should form. A 1-kilometer comet will make a 10-kilometer crater. But we don't really know in terms of the smaller stuff how often, we can't see it, so we don't know how often smaller craters form. There have been proposals to toss a big copper ball at Europa and fly through the ejecta, but people have concluded that most of what we'd get off is the water vapor, because the other stuff, there probably isn't enough of it, and it would volatilize much easier, and we'd probably end up measuring mostly water. So it has been looked into. Every once in a while on these studies, people say, hey, why aren't you throwing something at Europa? And, but to make a big enough plume, you'd have to bring a big copper ball, a mass is heavy to take with you. So it's a hard experiment to do. Plus, we don't know if it would show up results. There was an experiment, though, tossing a big copper ball at an asteroid. No, sorry, at a comet, deep impact, and looked at the plume that came off. So something like that has been done elsewhere. And then in the green shirt, yeah.
Recently, like the past 2 decades, maybe, it's been shown that archaea or microbial bacteria can synthesize energy using cyanide in some way. How that shifts your gaze at looking at light.
Right. Well, that's another example of the extremophiles, of the extreme environments in which life can flourish. So I wasn't familiar with the cyanide ones, but it doesn't surprise me too much, because when there's disequilibrium, life can live on it, right? What life wants to do is have some chemical reaction, make or have some way of providing energy to build ATP, right? That's all life really cares about, is something to power that battery. And so that's been some of the revolution in the last couple of decades in understanding these bizarre extreme environments, which makes you think, if we have liquid water out there and the possibility of chemical disequilibrium, how could there not be life? The problem is we don't really know how life gets started, how easy or how rare it is. And that leads to an important corollary here. If these places like Europa and Enceladus, if they're environments that have the ingredients for life, and there's chemical disequilibrium and the like, and there's not life, then that teaches us something very important too, about how much rarer life here on Earth really is. Another pitch for icy satellites versus Mars is, at Mars, if we were to find life there, the first question would be, is it the same as life here? That is, early in solar system history, there were enough large impacts that stuff got thrown between Mars and Earth. And so if life arose on one of them, it would have traveled to the other, which is why we could all be Martians. Right? It could have originated at Mars, been tossed off, landed on Earth, and then taken off here, or vice versa. It's really, really tough for something from Earth or Mars to get out to the outer solar system, out at Europa. And even if it does get there, it would slam into the surface so fast that it would just vaporize. So if life arose at Europa or elsewhere in the outer solar system, it should be an independent origin of life. And so if we found life there, we would be able to say, does it use the same chemistry? Does it use the same amino acids? Does it use ATP? Does it have the same handedness of molecules that sugars on Earth have, and that amino acids on Earth have? It would just revolutionize our understanding of biology and chemistry, biochemistry, if we were to find life elsewhere. So, unless there are any others?
I was glad to hear that you stressed the very high pressures that would be present in these oceans. And that's a self-serving one, because I once published a paper which really said that only at high pressure would you get sufficient stabilizing of polymers. You could make amino acids, but you couldn't get them to polymerize and stay polymerized for long enough unless you had high pressure.
Interesting.
You have that in every one of those outer moons that you've given as examples there.
Interesting. I wasn't familiar with that argument. I'd be very interested in learning more. At the bottom of Europa's ocean is similar to the Marianas Trench, the deepest part of Earth's oceans. And the argument I've heard as well, it could be really hard for life at extreme pressures, like in Ganymede and Callisto's oceans, though there's some evidence that life can, once it exists, that there's some Earth life where they've put extreme pressure and it's made it through. but I'd be very interested in following up on that, and learning about that.
It's easy to do.
Okay, thank you. All right, I guess we'll stop there. Thank you so much.